Okay, so now we have a tool, a very simple tool that lets us draw walls with simple lines. Now, the data analysis part could start to come in here. Let's say that we want to calculate the length of our walls because for some reason we don't want to have walls that are too long, or we want to have walls that are too short, or we want to have walls that are all different sizes. So we can look at the wall, which is the line we've created, and we can do an analysis onto it. Some basic analysis tools in terms of geometry are area or volume data. And in this case, since we're working with the walls, let's say that we're actually getting the average area of the wall, because that then the area of the wall is a function of both the height of the wall and the length of the wall. So I'm going to take the extrude component, which is creating the wall geometry from our lines, and I'm going to connect it to a panel so that I can just see what's going on. So we have 5 VREPs. I'm going to expand the canvas this way to give us some space. This is done by holding out and pressing the left mouse button. And I have 5 VREPs, so I'm going to then enter the area component, connect this to that one. So it looks like now I have 5 of the volumes and 5 of the walls and 5 corresponding areas attached to them. And then I can do some sort of analyses, basic analyses, such as average. This will give us the average for the items. So the average of all of these is 119,444. In this case, it looks like it's square inches because my model units is in inches. If I go in and change the units to, say, feet, then looks like I have enormous length of wall. In this case, let's go and say the wall height is actually just like 10.3 feet. Here we go. So now we have the total square footage of the walls being 1168 square feet. Average. Sorry, not the total. If we want to get the total, we could use this component called mass addition that adds all the numbers together. So then here we have the total. Now we can also do some things like standard deviation, which if you've taken statistics or math, or even if you haven't, the standard deviation is a measure of how widespread apart or how varied different numbers are. The lower the standard deviation, the lower the variance, and the closer they are to the average, the higher the standard deviation, the higher they're dispersed. And here's a basic formula. You take the average, you calculate the difference from the average from each data point, you square them, take the average of that square and take the square root. So what we're going to do is do that. So we have this list of numbers, and we have the average. So we're going to take the difference from that and the average. So we're going to subtract the average from the specific area. So we're going to get these values, which is the difference or the deviation from the average, and then we're going to square these values, which will get us the square root of the deviation, and then we're going to get the average of then these squared values. So I'm going to hook the average up, and then I'm going to take the square root, which gives us 298. So 298 is a measure of the standard deviation of these lines. That's how varied they are from each other. So now we have this Wallmaker tool, which is a very simple tool that just takes polylines created on a specific layer, extrudes them by a specific amount, and displays them as solid walls. Pretty simple. Now, I'm going to go in a little bit about the analysis of these geometry and how you can use analysis and manipulate data to gain either new insights about what you're creating, or create a goal or create a certain metric towards with which towards you want your designed tool to operate. So, for example, let's take this tool, which is a Wallmaker, and let's imagine that there's a given number of walls we can make. And as a constraint, let's imagine actually that because this wall is made out of certain material, there's only so much material we can use. So we're constrained by, for example, how much material we have. So one way to do that analysis would be maybe to take the area of the wall. And since we're dealing with this geometry, I'm going to go in and do that by creating an area component, plugging it into the extrude command. And what that gets us is it gets us a series of areas for each of the walls, which is great. Another thing we can do is we can find the average, and that will get us the average the average square footage of each of the walls. We can also do mass addition and add all the areas of the walls up, so we know that all the walls are 24,000 square feet approximately. And we can also do other analyses such as get the standard deviation. The standard deviation is how much the values spread from the average in some sense. It's a statistical measure of how dispersed, or how different the values are. So you see this kind of bell-shaped curve, which is a normal distribution. The further away, the flatter this curve is, the higher the standard deviation. And this is calculated by this formula, which is the square root of the average of the square differences, which is you take the average of all the points, or all your information. You get the difference between your data and the average. You square those differences. You get the average of those squares, and then you take the square root. And that's within statistics a pretty standard way to understand how different things are from each other. So we're going to actually try to do the standard deviation. I'm going to take the difference of each data point from the average. So I get these numbers. I'm going to then square all of these values, which is great. I'm going to then take the average of these squares. And then I'm going to take the square root of the average. So here's our standard deviation. This is great. I've taken these values and I've gotten the standard deviation. And you can notice that I can double check this by, say, one wall is standard deviation 0. If I create another wall that's very similar to it, the standard deviation is pretty low. It's 20, 56. If I copy all these over, standard deviation in fact doesn't really change. Then if I create something really small, the standard deviation grows to 544. If I create something really long, standard deviation also grows to 3163. So the larger the standard deviation, the more internally different all these lines are, or all our walls are. So you can imagine that actually the standard deviation is a measure of homogeneity, how homogeneous are our walls. And in fact, if these were not walls but actually floor plates, you can imagine that that would be an interesting way to determine variation within floors. So getting the standard deviation of the areas of floors would be a helpful way to tell you, oh, I want a building with various different floor sizes. Now, part of a very helpful thing within GSAPP is the cluster tool. And what the cluster tool does is it grabs a bunch of components together and wraps them into a package or a little function or a component in of itself. Now, the standard deviation tool is actually a pretty perfect way to use the cluster tool, because it's this thing that you might want to use in the future, and it's cumbersome, and you might want to, and you might not, when looking at this, know exactly what you're doing here. So the way to use a cluster is to surround a bunch of items, and to middle click and to use a cluster icon. But I'm actually not going to do that yet, because it's good when you're making clusters to clean up your component flow a little bit. So right now we have one output branching into two different inputs on two different components. I'm actually going to take that and consolidate it. So I'm going to get a data object, plug from the output area into this data object, and from this data object into these two components. So now it's very clean in this way that the data component takes the input and then distributes it to two separate components. And the end result is this value. So we then, if I delete that panel, and if I select this mass of components, you can notice that within this, there's one input and there's one output. So if I middle click and then click on cluster, then you notice a new component has been created that still outputs the same value, but now is vastly simpler or encapsulated in its own component. And now if I double click on this component, I've entered into this view. And this is very convenient, because now I can go in and debug or analyze what it's doing. And I can also click here, left click save and close, and jump outside. And I can just kind of rename this cluster to say standard deviation. I've added a hash at the front just because it's my habit, because at a glance I can tell what's a cluster or not. And the nice thing about clusters is that it's black boxing functionality. So I know that this is standard deviation. No matter, I don't have to really think about what it's doing. I'm just going to trust that I put in numbers into it and it gives me standard deviation. And that also means that if something goes wrong in the cluster, I can jump in and then debug or analyze the cluster without having to worry about what's going on outside. Also, the very fun or helpful thing about clusters is that if you copy and paste them within a document, if you hover over this, it actually says this cluster occurs 3 times. So it's actually the same cluster. So if I change one thing over here, let's say instead of the output being the square root, let's say the output is just 100. For some reason I want to have a cluster that just returns 100. So if I save it, then even though I edited this one outputs 100 also, this one outputs 100 also. So they're internally linked. And this is incredibly helpful when you're doing some operation that's really repetitive. So instead of copying and pasting a lot of components together, you can just make a cluster, copy and paste them. And then when you want to edit the behavior, you can just edit the cluster and it propagates across all of the other parts of your graph component. Now again, I'm going to go back in here and fix it, because we don't want the standard deviation to always be 100. And then the changes are reflected across all other clusters. So right now I'm getting the standard deviation, I'm getting the average, and I'm getting the values of each of the areas. So I'm going to try to find a way to express that standard deviation within the scope of the tool. So one good way to express the standard deviation could be to just write the text. You know, it shows up like text on the screen. So while I'm working on my interface, I also see the text change. That's one way to do this. And that can be done by using the text tag 3D. And so I could say, for example, I could get the center point of all of the lines. One interesting thing about the average function is that the area component or function, I'm using these terms interchangeably, the area component analyzes both the area and also gives you the center of the geometry. And the average component gives you an average of values, but if you, this is mass addition. But if you create an average component and plug geometry into it, it also gives you the average of all the points. Now this is partially because it's averaging the x values and the y values and the z values of all of these points, but it's also but it also is an accurate representation of what the average between all these points are. So this is a very handy way to get the average of a bunch of points. So I could take the standard deviation using our text tag 3D. I could set the location to be the center point, set the text, and I could also set the size because it looks like it's a little small here. Great. So this is one way in which I could display my standard deviation. As I make new lines, the standard deviation changes. Since the center of all the lines are changing, so does the location of the text. But this isn't that helpful, and especially when you rezoom out, it's hard to get a sense. It's not very intuitive, this reading of numbers. So in fact, what I'm going to do is I'm going to translate this number into a color, and then using that color, I'm going to represent or change how these walls are being colored. Instead of the text, I will take the standard deviation and I'll create it into a color. So say color spelled with a U, and there are many different color possibilities. I'm going to use color RGBF, which is floating point, and this color takes in 0 to 1 as an red, green, and blue value. Now it's clear that here I have the standard deviation of something like 33,000. So what I want to do is I want to map this standard deviation to 0 to 1, which means that I may have a possible standard deviation value of 4,000 or even 11,000. So it means that to some extent I have to define a range of standard deviation and map it onto 0 to 1. So I'm going to use the tool Remap Numbers, which takes a given number and using for one domain of a source domain, it maps it to a destination domain. So what that means is if I give it a source number, an initial value, it takes a source domain, so for example 0 to 1, and maps it onto another target domain. So I could give it a domain from 0 to 1,000 and it will map it on 0 to 1 and a proportionally kind of resize all the numbers that I give it to. So it wants a domain, so I'm going to type in domain and I'm going to create construct a domain. So this thing takes in a start value and an end value. So let's say my start value is 0. My end value is actually 10,000. So it says, okay, your sources, your values coming in are going to be from 0 to 10,000. Your your target domain, so your end values are going to be 0 to 1. So the remapped number, so the output we get is this. And right now you can notice that the number is actually larger than 1. That's okay, let's delete this line, for example. Then the standard deviation becomes 4152, and the remapped number becomes 0.4152. So I can use this, for example, to change the color values of the red and green colors. Then I could take this and plug this into the wall. Oops, I plugged into the wrong portion. I'll plug it into the shader. So now the wall is being colored according to the standard deviation of the lines. And let's see. As the standard deviation grows, it looks like the lines become darker, or sorry, brighter. So if I delete this really long one, the walls become darker. So as long as all the walls are dark, it means that my lines are roughly the same size. But if I start creating incredibly small walls, incredibly long walls, the walls become super bright. So this is a way in which visually I can immediately tell how varied my walls are, which is perhaps a pretty helpful thing to have in a tool. Another great way to use the Remap Numbers tool is if we want to represent within the tool, or the Grasshopper component, which walls are longer or have more area and which walls are shorter. So instead of plugging in the standard deviation, I'm going to plug in the area. So the values I'm going to map are the areas. In the source domain, instead of using this preset domain, what I can do is I can create, use this component called bounds, which takes a list of numbers, and then automatically calculates using the max and the minimum what the domain is. So if I plug this in, then what it's going to do is it's going to convert these values from this source domain from 227 to 68,000 into 0 to 1, and then it's going to plug these into the color value and then color each wall accordingly. And you notice it's already done this because it has 12 colors and 12 walls, and it's colored each wall according to those colors. So the longest wall is the brightest, or if I delete this, then this wall is the brightest. Which is interesting because I would have thought this one or this wall would have been longest, but you know, it's helpful in this way that now it's showing me. So if I continue to do that, I can also see the distribution. This wall looks the shortest for some reason, or maybe that's just a quirk of color. This wall looks the darkest. If I create a very short wall, this wall is definitely the shortest. So this is then perhaps a pretty helpful and simple way in which I can illustrate really quickly the different lengths of walls. What I can also do is, perhaps maybe I'm not interested in actually representing, I just want to find the minimum and the maximum length of walls. So I can do that by using the maximum component, and I can, which could theoretically compare two values, but actually the maximum component is not what I want because I don't want to compare just two values, I want to compare everything. So in this case the bounds component is helpful because it's getting the highest and the lowest numbers for us. So what I can do then is I can take the bounds, I can deconstruct the domain. So it takes the domain and gives me the two numbers that constitute it. And here now I'm getting the start 227, the end 91,560. Now I have a problem is I have a bunch of geometry over here, and I have their areas, and I want to find the component that has area 227, and I want to find the component that has 91,560. How do you do that? How do you sort or find or compare? If you're used to traditional programming, you might think, oh, an if statement. And if you're not, then you might just, want to say, okay, I want to kind of use a filter or something. Well, the actual default logic is within Grasshopper, or this kind of graphical programming, is actually to create a Boolean value or Boolean yes, no, true, false test case. So in this case, it's going to be an equals. It's going to say, okay, is the area equal to the start domain value? And what this is doing is, right now this area has 16 values, and this domain has one value. So it's going to go 16 times against this one value and try to compare. And what we're going to get is, according to this equal, this will be true if they are equal. So we'll get false, 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 true, false, false. So on the 13th, or actually the 14th comparison, we get true for the fact that this area, or the 14th value of the area, is of 227. Now then there are a few ways to isolate that geometry. You can imagine that we count, okay, we know it's a 14th number, and we isolate the 14th item. That's possible. But a better, quicker, and a more standard way is to use the dispatch component. So the dispatch takes in a list, and based on a list of true-false patterns, it dispatches them or divides them or sorts them into A or B. So if I give it the true pattern, then whatever geometry it takes in, it's going to shuffle the false value to B, and onwards, and the true value to A. So if we plug it into the area, plug the area into this dispatch component, then on the A side it's going to give us only the thing that matched, and the B side will give us only the results of the not matched. And of course it's going to give us 227 because that was the initial value we're asking for. So in this scenario what we're doing is it's saying, okay, look at all the areas and compare them with 227. Do they match or not match? Give us a list of when they matched or when they didn't match, and then based on that list sort this value. So instead of using the area, if we plug the geometry into dispatch, again what this dispatch will be doing is it'll be taking the list of geometry, which is 16 pieces of geometry in it. It'll be taking the true or false list, which again is 16 true or falses, and using that true or false list, it'll sort the geometry into 2 different lists. And so we get exactly what we want. Out of the A output, we're getting the surface of which area matches this number 227. So if I plug this A into here, this little teeny tiny piece looks like is the smallest piece of geometry that creates a wall that has area 227. Now I'm going to just move this out of the way so we can better see what's going on here. This dynamic of using a value, making it equal to something, or doing a comparison, it could also be greater than or less than, larger than, doing some sort of comparison, getting a Boolean list of true false values, plugging that into dispatch and using dispatch to sort it in order to get an answer. That's a very standard Grasshopper way to kind of do if statements, or to sort values, or to kind of grab certain values from another. So this is great and interesting. So now we have the smallest value, and again, why do we know it's the smallest value? Because from the domain, or from the bounds component, we've gotten the smallest and the largest values, or the lowest and the highest numbers. And then so we're comparing all the area values against the lowest numbers. Now we could do this again. We could say, okay, equals. We want to find an instance in which the area equals the end of the domain, or the largest area value. And then using that true or false list, we're going to dispatch and get the original geometry sorted according to the whether it's true, and then we're going to isolate this geometry. So it looks like this is supposed to be the longest, or the geometry with the most area, which is true. This is the smallest, this is the largest. And if I delete the largest, something else becomes the largest. And if they delete this, something else becomes the largest. Same goes for the smallest. Now then you can imagine that you can take these values and represent them with another preview component. So I could say, okay, I'm going to preview, use custom preview, plug these in as geometry, hold shift to connect two outputs into one input. And then I'm going to use the color picker to choose the color of these smallest and largest objects. If I disable the only draw preview for selected, and now this is an interesting way, and I can see what's our smallest and what's our largest. I'm going to hide these points because they're getting a little distracting. Again, a good policy to hide everything except for the preview components. Okay. So this means that now I can see this component and this component are my largest and smallest ones. If I delete this one, here it calculates what the smallest one is for me. So this could be a helpful design process, let's say, in which you just want to know the extremes of what's longest and what's shortest. In the meantime, you have this the colors, the yellowish to blackish colors, indicating the general gradient of how the ranking of how much surface area each wall has. So that's one way to do analysis, maximum or minimum, with the bounds component using the domain. And again, let's say this is pretty complicated, or it's just messy, it's starting to become messy, and all we want to have a component is to have a component that, given a series of geometry and a value, gets a maximum and minimum geometry based on that value. So we could do the same thing we did earlier, which is to create a cluster, and we're gonna clean this up. And the reason why I clean this up again is if I just take this and I create a cluster, I'm going to get within this cluster 3 inputs that all come from the same output. So in order to not do that, because it's a little messy, I can connect this output to this data component and just plug and replace everything. The same goes for this geometry, or this extrude component. I'm going to move this like that. And the last thing is, notice that this bound is also connected to here, and there's no way to clean that up. So what I'm going to do is I'm just going to copy and paste, actually. And I will plug this directly into the remap function, so that now I have this portion just kind of with 2 inputs, 2 outputs. I can middle click on it, click on cluster, and I can say get max min. And one of these is a maximum, one of these is a minimum. So then this is a very convenient cluster that takes geometry as input, and I can rewrite that. And it takes data as another input, and then creates a maximum and grabs the geometry at the minimum value and the maximum value. Which one is which? I can double click the cluster, go in. So it looks like this output comes from this, which comes from this, which is sorted via this, which is the start domain, so the smallest value. So this geometry is grabbing the smallest most value. So that's probably the minimum geometry. And this other one is probably the max geometry. That's another way in which I can do an analysis. Now, let's say I want to do something a little bit more advanced. Let's say this is all great and all, but what I want to do is I'm bored of, say, normal walls. And I want my walls to be as, the angles of my walls to be as irregular as possible. So let's say this is kind of right-angled wall, and this all has 90-degree angles, which I really don't like. And so let's pretend that my constraint for this tool is to say, okay, well, most walls are built at 90 degrees. I want walls, or I wanted to create a tool that creates walls in which the walls are not at 90-degree angles. In fact, I want the walls to all be at different angles as much as possible. Now, you might see where I'm getting. That kind of idea would mean that we would create a tool that analyzed all the angles at all the corners, and then grabbed or calculated the standard deviation for those angles, which would mean that if the standard deviation for those angles is very, very low, it might mean that all the angles are the same, where all the angles are 90 degrees. And if the standard deviation for those angles were all different, then it would mean that we would start to have irregular angles. For example, this wall where the angle is 45 degrees and super sharp. Whoops. Very sharp, then very obtuse. Another right angle, 60-degree angle, 30-degree angle, 90-degree angle, and so on and so forth. And this might be for us an ideal kind of wall because it has all these irregular angles, and moreover, it's not just repeating a 30-degree angle over and over. All of the angles are internally different. So this is an interesting kind of a brief that we've set up for ourselves. Part of it because it'll create interesting geometry. The other part of it is we're going to get into trees a little bit. So let's say I have this geometry. Now, I think in the first class we went over the idea of pseudocode, which is still a very, very helpful concept. And if we think about what we want to do, we want to get the geometry. We want to calculate the angles at each corner. Angle numbers. And then we want to calculate the standard deviation. Now this is great because we already have the geometry, right? We already have this wall, and in fact, for the angle, we probably want to use the polyline itself. So we already have this this geometry, and in fact, I'm actually going to just plug this in. So we have the geometry. That's great. Now we have to do something with calculating the angle, and the nice thing about this pseudocode is we already have the standard deviation. We've used the cluster that we've made earlier. So we could copy and paste it and plug it into here, which is excellent. So now all we have to do is calculate the angle of the numbers. Now because this is pseudocode and I just kind of mixed, I just copy and pasted, we're giving it a curve, not data. So ignore the fact that we're not getting a warning. But if you're following, you can probably understand that what this means is we want to have a function or something that calculates the angle of a line. So the way I'm actually going to go about this is another way of working with a Grasshopper. I'm actually going to make this into a cluster. And I'm going to say, I'm going to rename the output. Say line. And this is one way of doing using Grasshopper. And this is helpful because all I know is that this thing will calculate the angles given geometry, whatever it is, and I'll give you a bunch of angles, and then using that I can take the standard deviation of those angles. Now if I double click, I enter this view, which is the cluster view. And these components are pre-named. They're based on what the components were named before I clustered them. But if I modify this, then you can see when I click on this, within the cluster, Grasshopper is kind of acting like a normal Grasshopper component. So I can kind of do my work in here without thinking about the larger scope of everything else. And then when I save and close, then I can think about the larger Grasshopper component. So this is, again, a helpful way to think of, kind of localize the problem. I'm only thinking about this aspect. And, I can also create clusters within clusters. And you can go down, I've gone down as far as 6 clusters deep. You don't have to do that, but, it's possible. So what do I want to do? I want to grab the angles between these lines. So one thing I might want to do is I'll assume that this is a straight line. The polyline is a bunch of straight lines divided at corners. So one thing I could do is I could go into the curve component, or the curve panel, and kind of look my way around. There's a few things. There's shatter, which shatters a curve into segments. And then there's also, say, control points. Now shatter divides a curve into segments based on parameters, but we don't have those parameters. What we do have is we have the control points, and if we connect this line here, we get all the control points. Now, assuming we're not working with closed curves, we don't really need the first one because there's no angle, it's not between two lines. We don't need the second one. Sorry, we don't need the last point either. We only need the points in the middle. So one thing we could do is we could write something that grabs all but the first and last points and gets these points. And then we could do, for example, maybe some way to evaluate the line at a certain point. Now, and again, I'm kind of walking you through a typical thought process. This will not work, actually. The reason why being is that if you evaluate the curvature of a line right at this point, you're kind of in what is called like a kink situation, in which there's no curvature at this point. It's just an angle or discontinuity, so you won't get the right kind of information. But if you think about what an angle is, an angle is a measurement between two lines, and you can find an angle. Let's see. You can compute the angle between two vectors by typing an angle. So maybe actually what we actually need to do is to grab these two lines, and then these two lines, and then these two lines, and to kind of compare the lines in turn. Now then, what we can do is, instead of using these control points of shatter, so we can use the explode command, which is like the same explode command in Rhino, explodes a curve into smaller segments. So if I plug geometry into here, I'll get all these things, and if I look at what I'm getting through via the panel, I'm getting 6 lines, which is great because we have 6 parts. Now, another thing I want to do is then I want to compare the first one, the second one, and the second one, and the third one, and onwards. And how do I do that? One way that you can think of doing this, and actually the ideal way, is you can make 2 lists, and you can shift one. So by that I mean, let's say you have a list of these numbers. Actually, we call them A, B, C, D, E. And you want to compare A to B, B to C, C to D, and D to E. Now what you can do, and what the easiest way in Grasshopper, and there's a Grasshopper way of thinking, is you can take a list and shift it so that you're getting B, C, D, E, maybe A. Actually, let's just say you get a list that's shifted it, and you get a list that says B, C, D, E. Then you can take the 2 lists, and you notice you can compare the first part of the lists. So you compare A to B, B to C, C to D, D to E, and not compare the last component. So only compare the list 4 times instead of 5 times. Or you can compare the list according to the shortest list, right? So you cut the list off, the long list off, so you this one becomes effectively A, B, C, D. So this would be a way to compare the first one with the second item with the third item, third item with the fourth item with the fifth item. So how do we do that in Grasshopper? So we can use the shift list command. Actually, I'm going to continue this analogy here. So if I plug the shift list into here, this component shifts all the item in a list offsets, and it offsets it by 1, and if you set it to true, it'll wrap the values around. So if you look at what I get out, it'll give you B, C, D, E, A, which is similar to this, right? But we don't want to wrap the values. We actually want to stop it so that A doesn't come back around. So we get B, C, D, E. And again, we want to compare the two using the shortest list, or the shortest length of the list. And actually, there's a very helpful component in Grasshopper called shortest list that we can use. So then if I plug this list into here, I plug this list into here, what it does is it just compares the 2 lists and trims the longest list, so that you get then 2 forms of lists, so 2 forms of data that are the same length. And then this is exactly the situation we had earlier, where we want to compare A to B, B to C, C to D, and D to E. So I'm going to plug this directly into here. And so for these 6 curves, it's the same deal. If we plug this into shift, then what we get is these curves shifted. If we plug this into here, then we have 5 line-like curves, 5 line-like curves, and those would be the first curve and the second curve, and the third curve. Now, just because we're walking us through this this component, how do you know? How do you know exactly what you're getting? So a very helpful tool to use is list item, where you can grab the line-like curve, or sorry, you can grab a list, plug it into here, and what this item does is it retrieves a specific item for a list. So given the list and given the item, it gets the 0th, or the first item from the list. In Grasshopper, all numbers start with 0. So if I create a slider and plug it in here, it's going to grab me the number 3, or which is the 4th item in the list. So this will give me the first item, second item, third item, and you can see on the left the color of the lines are slowly changing. If you can't see it from the video, I'm just going to pipe the line just for clarity. So you can see that the first item of the list, second item, third item, fourth item, fifth item, the fifth item being chosen, but what's going on here is that this list item is actually also has a wrap component, so that if I just keep on going, I'll just keep on cycling around. If I turn that to false, I will get an error when I go too far, which is actually what I want, because I just want to see what geometry I have. So this is the list 0, 1, 2, 3, 4, and the other the other list that I'm comparing against, I'm going to copy and paste this so you can see what I'm getting, is now this one. So you can see that the fourth item in the list is the last one. So this is great, exactly what we want. So it's comparing the first and the second, second and the third, third and the fourth, fourth and the fifth, and fifth and the sixth. That's great. So again, the item is very helpful to debug, which is another term for to verify what you're doing and to make sure that what you're doing is right. So now we have two lines and we want to get the angle between them. And I'm going to type in angle. So this gets as an input two vectors. But now we have curves. So what do we do? Do we convert the lines into vectors? Well, actually, Grasshopper is very smart and it's very convenient. And so you can actually just plug the component directly into angle. And even though over here we have curves, which are lines, and here we have vectors, it automatically grabs a line and analyzes it and extracts a vector, which is very smart and very incredibly helpful. So in here, it's giving us the angle in radians. And if you're not familiar with radians is a value from 0 to 2 pi, or 2 times pi, which is analogous to 0 to 360 degrees. So I'm actually going to say, okay, give me degrees, which converts from radians to degrees. So pipe that into here. So get me a bunch of degrees, which is great. So it's telling me the degree between this and this is 81, this and this is 86, this and this is 122, this and this is 56, and this is 143. Now, this is normally great, except actually it's kind of a little bit off. You can notice that the angle between this and this is 81, looks like it, and this is 86. But these triangles is definitely not 122. In fact, it should be like smaller than 90 degrees. Same here. This should be larger than 90 degrees, yet it's 56. And these two are should be smaller than 90 degrees. It's 143. Now this is because the way the angle is being computed is it's using this line and this line and this line and this line, and each of these lines are different vectors pointing this way. So let me show you what I mean, and I'm going to delete this stuff. So in the process of converting the line to a vector, and I'm going to do this. And the other way that Grasshopper is very smart and helpful is that if I create a component that is just the vector component that collects vectors, and if I plug a line into the vector, it will automatically convert the line into a vector because it knows that I'm expecting a vector. It's kind of mashing the line and converting it into a vector. In programming terms, it's called casting, but you don't really need to know that. Incredibly helpful. There are some cases in which it wouldn't work. So if I convert a line to a number, actually that's incredibly helpful. I didn't know that. It looks like it's grabbing the length of the curve. Let me just double check if that's actually the case. Yeah, that's incredibly helpful. So just if you convert a line to a number, it gives you the length of the line. So Grasshopper can be incredibly helpful and convenient. Those are some little small tools and tricks that it's set up for you. So in any case, I have the vector. And if I look at these vectors, they're x, y, and z values. But that doesn't really mean much. So I'm going to use the vector display, which I need a point and the vector. And now these are lines. So what I can do is I can get the endpoints of the line. Get these guys. And so I can use the start point of the line as the anchor, or where to show the vector from. And I can show the vector. If I do this, So great, you can see that I have this line is going this way. This line is a vector going that way. Now let me actually do the same thing for the other lines we're comparing against. And I'm going to do the trick with the item again, the list item, where I'm going to, because I'm seeing all the vectors and it's kind of fuzzy and I'm not sure what's going on. What I'm going to do is I'm going to grab the line, use the slider, and then I'm going to plug this line into the vector and the endpoints component, so that, if you notice, I'm just looking at the vector of the first, second, third, fourth, fifth component. I'll do the same up here. So this way, for the first comparison, comparing these two vectors. Second comparison, I'm comparing these two vectors. The third, these two. Fourth, these two. Now, this is not ideal. Now, here's something interesting. What if we have two walls? Now, you'll notice something's interesting, that even if we have geometry that's drastically different internally, all the walls become the same color. Why is that? So we can start to kind of look into the logic. We can debug it by using the panel. Okay, so this looks good. We're getting 5 curves. We have 5 curves. And we're getting the angles. Now we're getting the angles, which looks pretty good. But you notice these horizontal bands, where instead of here where you just have items in a list, you have these, they're kind of divided into chunks. And this is actually a tree, or this is a series of branches that you're seeing. Each kind of divided chunk has a specific branch, and what you're seeing is a list at the end of a branch. There's actually another Grasshopper tutorial about trees that I've recorded, but I'm also going to do a kind of crash course on introduction to trees right now. So I'm going to use the Pram Viewer and plug data into it. And what it's telling us is, it says there's data with 5 branches. And this colon, comma, semicolon notation, which you also can see here, is a way of telling you how the data is structured. Grasshopper structures all data into branches, which is kind of a way of thinking of chunks and sub-chunks. You could imagine that you could have a data with 2 chunks, an A chunk and B chunk, and within the A chunk there's also an A1 chunk, an A2 chunk, etc. That kind of chunking and sub-chunking logic, Grasshopper is using the metaphor of a tree. So tree has 2 branches, and maybe a branch has 2 sub-branches and onwards. So the semicolon notation is a way of Grasshopper to say, okay, all this data, so for example 124 and 136 is on sub-branch, branch 0, sub-branch 0, sub-sub-branch 0. So the 0th sub-branch of the 0th sub-branch of the 0 branch. And if you take the Pram Viewer and double click on it, it changes the view so that you can see exactly what it's talking about. So right now all of the information, or all of the data, is on branch 0, which is the trunk in some sense, since there's only one main branch. And then within branch 0, there's 0, 1, 2, 3, 4, there are 5 sub-branches. So this is branch 0. There are 5 sub-branches, and you can tell that by what's going on if you zoom in, and it says 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. So this line indicates from the trunk, or from branch 0 to sub-branch 0, branch 0 to sub-branch 1. And then this further line going out that's another branch. So you can see that this is branch 0, 0, 0, 0, 1, 0, 0, 2, 0. So for some reason, after it's gone through this processing, we have one main branch, and off of this main branch there are 5 different branches. And off of these 5 different branches, each of these sub-branches has another branch. There's only one branch, and then at the end of the branch there's a piece of information. So again, there's one main branch, there are 5 sub-branches coming off of it. Off of these 5 sub-branches, there's another branch, and then at the end of the branch there's the data. So this is a visualization of what's going on here. Now, why is this important? Well, let's continue to debug what's going on here. This is important because the way Grasshopper uses trees is that it matches the level of branches. So if you have sub-branches, or say like a first level branch, a second level branch, it'll try to compute the second level branch with the second level branch or something, or similar. It'll match the branches up together, and that's a way in which you can regulate which chunks are computed with which chunks. So it looks like the data, when it goes into the standard deviation node, or the standard deviation component, is actually computing within each branch. So what went in was the first branch, or the first branch, sub-branch piece of information, came out with the standard deviation. So it's doing it internally per branch. We're not getting the standard deviation for all of the values. So after the remap function, those values are also being mapped. We're also getting different colors. And so what's going on in here is that the preview component gets 5 values, and I'm also just going to plug that in so we can see what exactly we're getting. The preview component gets 5 values, but they're all in a list. And the color component is giving us all of these values, but they're on separate branches. And when that happens, what Grasshopper will do is it'll take this branch, or it'll iterate on this list, actually, and it will iterate on this list across all of these values. So it'll color the first open brep with 15, 15, 15, the second brep with 15, 15, 15, and the reason why it's doing that is I'm going to open the Pram Viewer and show you graphically. Grasshopper operates on lists, and when it has one list to many lists, it just or it operates between items. And so this item of geometry and this item of geometry, there's an operation that happens between those two, and this item and the second item of geometry, and onwards. But this item is really a list, and this item is really a single color. So what happens is when Grasshopper computes this item and this item together, it's actually computing between 5 items in a list and 1 color. So which is why if you hover your mouse over preview, the component ran 25 times because it's doing 5 once, 5 again, 5 again, 5 again. So it's doing that 5 times. So that's why the component is running 25 times. But so that's actually not what we want. And okay, so we have 5 values. We might say, okay, we actually want to color that list according to these 5 values. One way we can have this match up is we can use the Flattened Technique, which is also a separate component. Plug it in here. And what that does is it'll flatten all the branches into one, kind of in order. So the first branch, first item, second item, third item, they're just smashed into one list. And so if we connect this to the preview, that works great. So we can see that the lines are colored differently. Now the other option is to graft the other input in the preview. So I can use the graft command. What that does is it takes every item on the list and makes it into its own branch. So now it has these 4 branches, and if I plug it into the Pram Viewer, that looks like this, right? So it has one main branch, 4 branches, and then 4 items hanging off that branch. The red is the item or the list, and the green is the branching tree structure. Now if I plug that into the preview, and I hide these, and I undo the flatten, my mistake. You can see a similar thing also happens. So we have 4 values and 4 values here, and they're in different, they're both branched out. And so what Grasshopper will do is it'll match this branch with this branch, this one branch with this branch, and onwards. And this is because the branches are on the same same height, or the same kind of complexity, or the same branching structure. This is trunk. The first item here is trunk 0, sub-branch 0, sub-branch 0. This is over up here. It's branch 0, sub-branch 0. But because they line up, it's coloring the first geometry with the first value and onwards, so on and so forth. Okay, so you can also watch the other tree video that goes into this a little bit more in depth. But suffice to say that because we have 4 branches, or 4 items at the end, and 4 items at the end, Grasshopper matches this up, or tries its best to. And so you can notice that the component ran 4 times, and each wall is colored separately. Now, one thing about this component is that it's grabbing the values, or the angles internal to itself. So if I have an interesting wall, let's say it's this formation, if I keep on continuing it, Grasshopper, this component really likes it, even though it's starting to become incredibly repetitive. So it might be that actually what I want is not the standard deviation of all of the angles within a line. It's actually the standard deviation of all the angles in this world, in this geometry period. So the standard deviation, this cluster is taking in 32 values, but as these 16 branches, and then it's giving us 16 branches as an output. So one thing I can do is I can say I can use the flattened component. There's also a flattened component by right-clicking and clicking flatten. What it does is it flattens all the geometry into, or all the information to one list, one flat list. So it just takes this and adds them all into each other. So the flatten, you get just like one large tree. Very refreshing, very dangerous, or not dangerous. It's very, it changes your data. It can change your data a lot, but it's sometimes very necessary. And so if we plug it into the standard deviation, we get one answer. So then you can take that answer and then color everything. And over here, we're getting 16 branches, and we're using one value to do it. And it's okay, we don't have to flatten this or anything, because if we have 16 branches and one value, it's going to try to use this one value into all 16 branches, which is what we wanted to do anyways. So that way, it's going to start to calculate the standard deviation of the entire script, or of everything. Which is interesting and good and helpful. And perhaps this way, we wouldn't just be able to get away with the same wall repeated over. We would have to have all the walls be at different angles to each other. And that would be a good kind of way to calculate. You can notice that if I copy this multiple times, it starts to become the same color because the standard deviation of all the angles are getting lower, because I'm making more and more of the same. So this is maybe a good way in which I could try to make a design of a floor plan, or some other form that has all these constantly different angles. So has as many different angles as possible. And note that this is done with the standard deviation component, or which we made. And so the standard deviation is a tool to generate diversity, and depending on what you apply it onto, you can imagine that you use the spider sack example, or use any form creator to create clusters of form, and whatever you apply it onto, it's a way to kind of map or visualize or calculate variance, which is then has spatial impact. In this case, the more I want to try to make geometry that makes these walls become brighter and brighter, the more I'm kind of designing towards a kind of a more varied floor in which all the walls are angled at different angles. And as we did earlier, you could imagine that taking the average of all of the walls gives you, another interesting or different metric altogether. You could imagine that I could possibly plug all the segments or the lengths of the segments into Grasshopper, and want to keep an average too. And that way, I would be kind of pulled between having similar lengths, or having similar lengths of walls that on an angle level are different as much as possible. So that's one way in which the analysis of the data creates a form, or a metric that then creates a form.